All right, cool. I think it's about noon. This is Anti-Forensics AF. If you're here for a different talk or something cooler than Anti-Forensics AF, you can go to one of the other cooler talks. Or stay here, choose your own adventure. That's cool. My name is int0x80. I'm the rapper in dual core. I've done a number of anti-forensics talks here at DerbyCon. I'm very happy to be back. This is just like a bunch of trolley stuff. Like I get on the computer and I'm like, what happens if I do this? So first we're going to talk about some memory forensic stuff, basically from the point of being a malware author or like an attacker on a system, and you've got your malware is running and you want to maintain on the system without being acquired or analyzed. And so to do that, we're going to use some self-modifying code, and we'll look at an example with Windows and Linux. And then we'll talk about some Android stuff. Oh, shoot, which reminds me. I need my Android phone. I should have prepped that. And then I've got some really cool stuff. We're going to play a CTF with SD cards, and it's super fun. It's like a really cool trick I found that I don't think many people have seen. Oh, thank you. Shouts out to Uda. Make noise for Uda, please. All right, cool. So just lots of fun random stuff. So this is my who am I page or whatever. I don't do forensics for a living. I'm on a red team. I come from a reverse engineering and malware background. I love to just mess around and see what happens. So that's the trollolol part. I've had some really interesting trollolol experiences with some three-letter agencies like the FBI and most recently the NSA. If you want to talk to me about that some other time, I'd be happy to talk to you about it. I'm not an expert at all. Like I said, I just mess around, so your knowledge may vary. And pretty much all the cool things I've learned to do with computers are illegal, so do illegal things. Okay, so our focus on the memory forensic side of things is that we are an operator or an attacker on a victim system. We've got our own malware that we've built, so we've invested a lot of time in our own tool chain, customizing, making stuff that's never been seen before. We're potentially APT, and we want to persist and thwart detection. So we don't want our malware to get picked up. We don't want it to get acquired. We don't want it to get analyzed. So we're going to work against that. And so we all know, last 10 years or so, the hotness has been memory forensics, right? Disk-based forensics is dead. So we're going to leverage that to our advantage, right? We're going to take advantage of the fact that we can do some cool things in memory that help us as an attacker. So in the example of malware, on disk, you have a bunch of sections in your executable file. And to get from disk into memory, you need all of those sections. All of the analysis tools also need those sections, but once we're in memory, we may not necessarily need them. So we're gonna take advantage of that. So it's pretty cool. By manipulating our executables in memory, we can totally troll the analysis tools and have a good time. So this is a program that I made called "The keys are right next to each other." It's taken from a bash.org quote. And actually this is pretty much, I think, the last demo that I left off with in my last DerbyCon talk. But I ran it under XP. It was a few years ago. So I was just curious to see, does this work in Windows 10? So in this case, we're going to use Recall, which is a free framework from Google for doing memory forensics. Pretty dope. If you haven't checked it out, A++, would recommend. Would clone Git repository. So let's see, we've got, there's our malware. It's just running, just doing evil stuff as it does. Now, oh God. Okay. In a separate tab, let's run recall. Or we use WinPMem first, and this is going to do our acquisition of RAM. And now this takes a while, so I thought I'd play a video for you guys while we wait. I found this series recently called "You Suck at Cooking," and it's kind of cool. It's almost like the how-to basic videos, but with some dry humor. So without further ado, this is how to cook corn on the cob.
Shucking, it's a fancy word for peeling, and how you shuck is a personal choice. The traditional method is to grab the husk and shuck downward. Repeat this motion until the cob is husk-free. You can also up-shuck it. These methods are hard work and you end up shucking yourself silly, so consider trying the golf shuck. Corn! Or you can try playing shuckminton. Or you can use a comprehensive spinning wheel dual momentum shuck system. Or you can bucket shuck it. You can throw it against a rock. Whoops, don't throw it against a rock. Or if you're quick enough, you can do the falcon shuck. The Shuckatron 6 is new technology that's based on particle theory and magic. You just slide it through there and just make sure to wash the particles off of your corn after, because particles aren't good for you. And if you don't like corn on the cob, you can take a hammer and get corn off the cob. Or you can buy this corn I've been developing with Monsanto. It's cobless corn, and the way we make it is through genetic engineering, and it's perfectly healthy and safe, we're pretty sure. Or you can try this corn sausage we've been making. It looks and tastes like real turkey sausage, and the way we make that is by having a turkey, a cob of corn. To cook the corn, a lot of people think you just fill a pot with water, boil the water, throw in the corn, add some salt, let it cook for a few minutes, and then it's done. And those people are correct. Applying butter to your corn is also a personal. Rookies will use a knife, which is a sloppy way to go about it, and it leaves your corn tasting like butter and metal. This is the classic way. You just gently roll your cob in the butter until it's coated. A more advanced way is to take a slab of butter and carve a cornhole into the side. Slide your cob into the cornhole and twist it while moving it in and out until your cob is completely coated with butter. If your cornhole isn't big enough, gently twist it with perseverance until it slides through easily. You can also stick butter onto some tongs, tape those to a broom handle, and butter your corn from a distance. This is a great technique if you suffer from a strong fear of corn. Buttered corn can be slippery, so be sure to attach a handle like this 2.71A Phillips screwdriver. I just made up the 2.71A part. But yeah, that's corn on the cob, and it's more delicious than corn on the log, or corn in the bog, or corn on the saw, or corn on the dog, or corn in the fog, or corn on the job, or corn in the clog, or corn on Bob, or corn on the slob, which is the same thing. Get your shit together, Bob, seriously. And it's obviously best eaten as corn on the knob. And if you're sick of corn, consider...
All right, so that's, you suck at cooking. Oh good, and our acquisition's done, all right. All right, so let's run recall. And let's see, we'll pass it. This is our acquisition file .aff4. It's like its own format, but recall understands it, so it's good. And basically what you get is this IPython notebook workspace, right? It's pretty dope. Like, I don't know if anybody uses IPython, but it totally changed my life. Before it was just me Python. So what we're going to do is use a proc dump module inside of recall. And like if you've ever used volatility for memory forensics to extract a process, you need to find the PID first, right? In this case, we can just say, oh yeah, the process looks something like this, the keys, and then we can just specify the dump directory. And all of this is like tab completed, just like IPython stuff is, which is super nice. All right, so it looks like our directory dumped, or nope, it did not. It didn't like that. Maybe I should try using tab completion. Oh, come on now. That's totally right. Oh, I forgot a comma. Psh. Get your shit together, int0x80. All right, cool. So while it's doing that, let's look at what the original program looks like, right? So, hey, I found something weird on this system. Like, let's echo 22 and see what's up. So, oh fuck, you know what? Bam. So this is, normal IDA Pro, load a program in, looks legit, right? You get a cool call function graph, function names are all good, everything good, right? Cool. So now let's take a look at our dumped executable. So here's our dumped executable. Oh, doesn't really recognize it. Let's just go with the default, see what happens. That doesn't look right. Notice we've got like a lot fewer subfunctions on the side. These instructions don't look right. They're like 16-bit. Strange, right? If you're a malware analyst and this is what you get to work with as your starting point, you're going to be like, WTF, mate? Like, what is this? And I don't know about you guys. I personally don't know any forensics examiners that know IDA well enough to go through and start marking things as code and put the time in. But if we go back to our original tab, our malware is still running, right? So we're still doing evil stuff. So we've thwarted analysis, and that's pretty cool. So, yay, attackers win. And then let's take a look at the source because it's pretty easy. So this is very like basic proof of concept. We get a handle to the process, make sure that we're dealing with a Windows executable here. So here's our checks for 45A, the MS-DOS stub, and then 50 null, the PE header. Process the sections. We're going to use virtual protect to add write permissions onto the header of the executable file in memory. And then we're going to call RTL0 memory, and this is like the thing that does the special sauce. And what it does is it just writes zeros into the header in memory. So that makes it so that when you grab the executable out, you just get like no information about what your bytes are. We restore the page permissions with virtual protect, and then here we just loop for proof of concept demo purposes. Any questions at all about the keys are like right next to each other? Yes, in the back. Yeah, so the question is about volatility plugins, and there is a proc dump plugin in volatility. When I did it in XP, it also failed. And so recall was the new hotness, and so I just built a demo for recall in this particular case. I haven't tested it for against new volatility in Windows, so it might have better success. I just tested against recall because I was like, hey, Google Smart Pros, like it should probably work, and then it didn't. So I was like, hey, good job, me. Mm-hmm. Yeah, when I did it in Windows in my last demo, like in XP, I won against volatility. And we'll actually do a demo against volatility in Linux, and spoiler alert, I win again. So yeah, again, this is, we don't need the PE header after we've loaded. We can do whatever we want. If you really want to have some fun, try writing weird values into the PE header and then loading your dumped executable into analysis tools. You might get some crashes with some interesting values and some registers, just if you're into that kind of stuff. So pretty neat. We win, and this has worked all the way from Windows XP up into Windows 10. For completeness, these are the commands that I ran. If anybody wants to like take a picture of the screen, but it's pretty straightforward. It's just win pmem to acquire the RAM, and then run recall against the acquisition, and then run the proc dump module inside of recall. All right, so let's try it in Linux, and we'll go against volatility, and we'll use Lime for the acquisition, which is an open source kernel driver. Password is my luggage combination. All right, so here's our Linux variant. So we found our elf header. This is just debugging output. You could do whatever you want here. So now we're doing evil stuff as we do. All right, so cool. Let's get Lime first. Cool, we have a build. If you want to build Lime for your kernel version, you just run make. It should build straight away. So we need to load my Lime into memory so we can do an acquisition. KO. And there's a couple arguments you specify. So first you tell it where your path is to store the acquisition. So let's just tell it like lol.lime and under temp. And then you can specify a format. I think the options are like lime and raw, but volatility understands the lime format, so we'll just do that. 5500 for my password. Just kidding. Okay, cool. So we should have our RAM acquisition. Cool. And again, malware is still running, so malware should be in there somewhere. We can grab it. So let's see. I'm not going to go in depth, but I'll show it in the slides. There's a caveat with volatility on Linux. It doesn't come with a profile for your build of Linux, so you have to build your own profile for any system that you're going to be doing memory analysis on. It's a pretty straightforward process, and I'll cover it in the slides rather than walk you through it here in the demo. We'll just get to the cool stuff. So, and you can test it if you've got it by doing something like this. Use the --info flags, and then just grep for Linux. And then that'll tell you you've got to show your profile once you've installed it. All right, so let's get our malware out of RAM, because we know that attackers are on the system. So we have to specify our profile to volatility so it knows how to do the thing. And first, like I said earlier, you have to get the process listing or the PID for your target process that you want to dump. So here's our PID of 2221. And we'll use the proc dump module and specify our PID, 21, bam. Ignore the destorm stuff, it's just I don't have those modules installed. Okay, cool, looks like we got a dump. All right, blue team is winning, here we go. Let's hex dump it. Oh, we didn't get anything. Well, how big is the process that we dumped? Oh, it's 0 bytes. Wah, wah. Empty. Hey, and our malware is still doing evil stuff. Good job, red team. Woo! So basically the same. Same setup going on here. We basically find our header in memory. The way I do this is really bad, and I should feel bad, but it's easy and it works. So I'm just using proc self maps, and you might be on a system that you don't have access to proc potentially, so don't rely on this. But I'm lazy, so using fscanf to find the entry for my header, and here we use mprotect, whereas in Windows we used virtual protect. We set our page write permissions so that we can modify the header. Here we use memset instead of RTL0 memory, and then reset the page permissions using mprotect again. And then here's just our debugging stuff. Whereas in real life we'd be catching shells and exfilling data and getting bitcoins. Cool. All right, so that was the Linux one. Oh no. Sorry. Okay, now we're good. I forgot about the goats for a minute. Okay, so pretty much same thing that we walked through here. We don't need the ELF header, just like we didn't need the PE header. So we can zero it out, or if you want to, you could tamper it and add in weird values and get really interesting register values sometimes. And then this is like the full process. I can send you guys slides if you want. They'll come as a PDF, no malware, I promise. Git clone Lime from GitHub, build it, insmod it so you get it running in the kernel, get volatility, install it, and then this is the profile build stuff. So you'll cd into this like tools Linux subdirectory and just run make, and that'll produce this module.dwarf file. And if you run head on that, you should see .debug info at the top, lets you know that you've got it built correctly. Then once you've got your module.dwarf file, you'll need to package it with your current system.map and place that zip in the directory under plugins overlays for volatility. And then at that point, you can check that it's installed correctly with that python.vol.py info grep Linux that I showed earlier. And then we just did pslist and procdump, and it didn't save us in this case, but that's the completeness. Ah! All right. So Android stuff. Any questions about either the Windows or Linux variants for the keys are like right next to each other? Cool. All right. Android stuff. So my girlfriend and I were interested about Android stuff a little while back, and we didn't know anything about forensics for Android, so we're like, hey, let's figure it out. So these are some things that we figured out. So all of this is based on the premise of using encryption, encrypting your device. Also, to quote the Gruck, use Tor, use Signal. I don't know if this one shows up as well. I want to eat a pint of Jerry Garcia ice cream. Should I use a bowl or not? Use Tor, use Signal. And then selling social security numbers for Bitcoins, contact me on my XMPP. I guess I don't know if I should admit or not, but pretty much the reason that I made this talk was because I had the idea to use screaming goats for the slide transitions, and I was like, what can I put around that? All right, so let's talk about forensics real quick. I'm going to try to push through this part pretty quickly, and I can talk to you more in depth about it afterwards, but really I want to play the CTF with y'all for the SD card stuff because it's really fun. So first, Android forensics. Okay, so Android forensics, not the easiest. There's like a bunch of stuff you have to have in place. Also, it's like a weird setup. You have to cross-compile netcat for ARM and then load it onto the device that you're doing an acquisition from. So like if anybody's done like hardware forensics, or like hard drive forensics, you usually use a write blocker and you don't write anything onto the device that you're acquiring from. In this case, you're pushing a program that you've built onto a target device that you're about to acquire from. Really weird, but it works. You need the device to be powered on, decrypted, unlocked, rooted, and have USB debugging enabled. So that's quite a lofty kill chain, right? You stop any one of those things and forensics fails. And then if you want to do memory forensics, you need loadable kernel modules enabled, which on all of the Android devices that I've seen do not have that enabled. So good luck. I guess I could live on a farm as long as they have internet and goats. Okay, so basically what you do in Android forensic acquisition off of the NAND storage is you push your compiled netcat binary onto your target device and you set up a port forward. And then you invoke a shell, get root, and situate your netcat binary, give it executable permissions. You could probably do like 755 if you wanted, but YOLO. Then you DD, this is all familiar to us, right? DD off of the NAND storage, block size 64K, no big deal. And then pipe that to netcat and send it across the USB using netcat. On the receiving end on your laptop, you'll have a netcat client that'll connect into the listener on the phone, and then you'll just grab all that data and store it off into whatever you want to call your file. In this case, I call it image.nand. Then standard forensic stuff, checksum it, make a copy, checksum the copy, etc. Another weird thing I found with Android stuff is that you'll find the NAND storage exposed via different interfaces. It just varies per device, it seems. So like these are some that I've seen it under. Just look at the proc partitions on the system, and that'll tell you like where the storage is. So it might be under dev block or dev mtd or dev emmc. And then I was just trying to be clever with that C++ line at the end. Sad. So in the situations where you can't like get root and do like a full DD acquisition of the NAND, you can get some other logical acquisitions, right? ADB pull is basically like trying to do like a CP of slash onto like your local storage. So it'll grab whatever it can for you, and in this case we just have like a local directory called dump that we're going to dump onto on our laptop. There's also this like dumpsys program. There's ADB backup, which you have to add a pin for. You have to have the pin for the phone or the device in order to use ADB backup, which then puts it in the bash history. So if you're targeting the forensic investigator, you can find the pin of the phone. There's also dump state, bug report. These things get you like logs of like various radios that are on the device. There's an open source tool called AFLogical OSE. There's a law enforcement edition of it as well. And I don't know the differences between the two, but the open source edition is out there if you want to mess around with it. So TLDR, it sucks. Like Android forensics sucks. Would not do again or ever. And it's weird that it violates the traditional forensic methodologies to me, right? Like you're writing onto the device you're about to acquire from. It's mind equals blown. And then that kill chain we had of things being like powered on, decrypted, all that stuff, it's super easy to disrupt. It's not even a goat. All right, so here's our setup, is we have our Android device and we're using full disk encryption, and maybe we're out like in the raided by law enforcement scenario, maybe we're out freedom fighting as the Gruck calls it, we're out operating somewhere. You always, of course, leave your phone at home when you do that. As my girlfriend has pointed out to me multiple times. And so let's say you're out operating and you come home and, oh, there's a bunch of police at my house, like what's going on? You don't want the police to acquire your device at home and then get evidence off of it. So, or like as a separate situation, say maybe you're deploying a hardware implant on an operation, and if blue team or law enforcement or somebody else that's not ever supposed to find the device finds the hardware implant, you don't want them to get any evidence off of it. So, and then this last one I was like, shrug is like, you know, there are other scenarios, but I can't think of any. And then I looked at it and it looks like Kah's throwing a phone to me. So, you know, you want to encrypt your device if Kah's is ever touching it. Don't ever let him touch your phone. Okay, so I'm thinking like we're using using encryption, right? The easiest solution is just power down the device if you think you're in danger. I mean, it's not destructive. Your data is still intact in the event that you're not actually being raided by law enforcement or something. And then you've got everything, your evidence is all encrypted. And then, of course, lawyer up. You know, don't ever talk to the police. So what can we do to leverage or to see like whether we're being tampered with? We have all these sensors at our disposal, right? Bluetooth, pair my device with another device in my house. If it becomes unpaired, turn it off. It's encrypted. It's on the cell network. If law enforcement comes in and acquires a device, they're probably going to put it in a Faraday bag, and that's going to stop any transmission and receiving, right? So if it goes off the cell network, power it off. It's encrypted. GPS goes outside the geofence of my property, power it off. All this stuff. So we can use all of these to like leverage or figure out whether we're being tampered with and consequently turn the device off to protect ourselves. So I wrote this app called Duck the Police, and I'd like to do what I hope will be the worst HackerCon demo ever for you guys. So I have this Android device here. Running Duck the Police, and we're going to set it for movement, and we're going to say Duck the Police. And I'm just going to set it down, and I'm going to pick it up, and the phone is off, and it's encrypted. So, Duck the Police, and I will accept Pony nominations for worst Hacker Conference demo ever. I'll put the Pony Award right next to my other two. It'll be in good company. So. I was surprised at the lack of Duck the Police memes that were on the internet. That one I especially like because I used to work with a guy who's really good at lockpicking, and he was like, oh yeah, I can pick the boots on cars, like no problem. And he's like, the police charge you like $125 to take those things off. I charge $75. The bubble tape one just killed me. I love that one. All right, so yeah, we're using encryption, and if we leverage like motion sensors or like accelerometers in the device, it moves. If it's like recovered by somebody we don't want it to be recovered by, it powers down, we win. Good to go. All right, SD cards. All right, so if you've seen this talk previously, you're not allowed to play the CTF, sorry. Let's do SD cards. I'm just going to go back and forth. I love that song. Okay, so I have an SD card here, and I'm going to plug it in, and we'll take a look at it. There it goes. All right. The rules of the CTF, something, 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 can't read from this angle because privacy filter on my screen. Enter your name below. So basically the TLDR is we need to add our name to this text file, we need to save it, we need to unmount the file system, remove the SD card, add the SD card back in, and make sure that our name is still in the file. Seems pretty easy. Okay. There's my name, right? Cool. int0x80, yeah, all right. Let's unmount it. SD card is out, SD card going back in. File still there. Oh no, my name's not there, but the file is. Okay, what can we try? The what? The file system? Let's look. Extended to. I'm sorry? Immutable bit? Okay, so like add our name and then do like change adder plus I on it. Okay, I like that. Okay, int80 is there. We're good. Immutable bit is set. Also, all right, there it is. I. Let's unmount it. SD card's out. SD card's back in. There's challenge.txt. Oh no, my name's not there. All right, what else can we try? Like with a hardware switch, or okay, so the premise is that the hardware switch is off. I guess I should have specified that. It's not hardware locked. Okay, sorry, and I heard something over here. Yes. Which U mount? Okay. It's bin U mount. I'm not trojaning U mount, so it's standard U mount on Linux. Yes. I'm sorry? Rename the file? Yeah, let's do that. So, adding int80, cool guy. Or do you want to just move it? How about that? Stop. Let's call it pancakes. Okay, pancakes is there. int80 is still there. Let's U-mount it. SD card coming out. SD card going back in. Oh shit, it's challenge.txt again. Oh, wait, that's right. And my name's not there still. What else? In the back. Oh yeah, we did which mount. It's bin mount, and it's the standard mount that's included in the distro. Yeah, no, didn't tamper that. In the back. Yes, and we can double check the mount flags. So here's our RW. So we're read write. Yes. We can. I'll go ahead and spoiler alert for you because it'll take longer than is left in the talk. That doesn't work either. But good. This is another thing that I tried. Yes. Nope, I'm not using any UDEV gnarliness or anything like that. Sure. Let me see it. Because I'm cool like that. Lost and found is a standard directory on extended file systems. Yes. Yeah, let's check partitions. So this is our device, MMC block 0. Nope, just the one, P1. Yes, in the back. I am not using an overlay on the file system, but good. That's a good one. Yes, in the back. Yes, there is something on the SD card itself. Way to go, we worked our way down the stack. So, There's a program called SD Tool, which will allow us to interface with the firmware on the SD card, and we can change the write state as to whether or not we can write to the card. So what's awesome is the way that this gets displayed to the operating system above is that everything's fine. No errors, no permission issues, you know, everything looks good. We mount and you mount, no worries at all. And, but under the hood, we're preventing the writes. And this tool is open source. I don't know if I mentioned in the slides or not, we'll see. But basically all I did is change the makefile to use Clang instead of GCC. But yes. But the lock switch is set to like allow writes. Yeah. I don't know. Whoever figured this out just figured out the interface to make it do the thing. So there's a few commands. Yeah, like I said, I'm not an expert. I just mess around on computers. So here with the status, we can see that the write state is on temporarily. So we can update the write protection state. So now the write protection is off. So we'll unmount it. Card's out. Card's going back in. It's that boy. Oh shit, what up? So shouts out to Craig Smith from Open Garages. He's kind of the one that got me onto this track and figuring this stuff out. So it was a really cool trick, and I think it's a pretty neat thing I hadn't seen anywhere else. Oh, balls. Bob Saget. All right. That was just in case I wasn't paying attention. Whoa! That was in case you weren't paying attention. All right, so using this open source tool, SD tool, we're able to lock and unlock the device and also check its status as well. Again, the physical lock is disengaged, so to anybody recovering the SD card, you know, they're going to be like, yeah, you know, looks fine. All this stuff happens in memory, so we're good to go. Nothing gets written to the device, aka no logs, no crime, which is awesome. Caveats. So USB hub does not present itself in the same way all the time as an MMC device. So you might need an actual like SD card reader that's not connected via USB bridge. So I think some of them might work. Also, I've like run into just like hit or miss with certain cards. Like this micro SD card inside of the SD adapter works fine. Other micro SD cards I tested did not work. So just ask your friends for some totally safe micro SD cards and then give them back. So my ideas for like the example scenarios are like you've got like a hardware implant, right? You're using on an active operation. I've actually gone against the red team engagement where they used an Android device implanted in the facility, and we recovered the Android device and we ripped the malware off of it, and I RE'd the malware, and then we were able to pivot off of that and go find more infected nodes on the network. But had they used a mechanism like the Android stuff or whatever, they could have potentially killed that. Or like use that with the SD card, excuse me, and I wouldn't have been able to get anything good off the SD card. Also, if you guys use like Raspberry Pis, right, like those run off of SD cards, so totally do this to your SD card, put it in your Raspberry Pi, build a portable Pi or whatever you want, and if it ever gets acquired, you're good. Nothing ever got written to the device. And then if you want to try like running your attack VMs or your attack platform off of an SD card and boot off of it, like nothing gets written, right? Run a laptop, no hard drive, no other persistent storage, just an SD card that also does not do persistent storage. It's kind of neat.
I still don't know what this. What is that?
He's there. He's hiding.
What kind of animal is this?